Hi. Last time we looked at how to look at defining the equations of motion for a single degree of freedom, which is a generalized single degree of freedom. We saw that essentially the kind of systems that we look at were assemblages of rigid bars, and the entire system had one degree of freedom. Now, was a single degree of freedom system, and the overall point was that what that degree of freedom, we saw many problems in which there were at least more than one degree of freedom that could be defined as a single degree of freedom. And of course, if you use that as a generalized displacement quantity, okay, then the equation of motion corresponding to that generalized displacement quantity was different from another one which was using another degree of freedom, but essentially they were relatable to each other based on the relationship between the two generalized single degree of freedom generalized displacements. Because if it is a single degree of freedom system, you always have one unknown, and obviously any other thing is related to that one unknown. Okay? So, we saw that. Today, we are going to be continuing to look at generalized and equations of motion. The only difference is that we shall be looking at essentially systems which are not really single degree of freedom systems, but are rather they are actually multi degree of freedom systems, and in fact, we will see that they are actually continuous systems which we can consider as a single degree of freedom problem. Let's see how this is. Let me draw a cantilever, and this cantilever, I am going to say that when it deflects, what happens? Okay, it's going to deflect like this, and if I look at if you look at this is with x. Okay, so this is u x of t. Now, what we say is, look, this u of x of t is given by a xi x times z 0 of t, and z 0 of t in this particular case I will define as this displacement, right. So, that is z 0 of t. The degree of freedom is z 0 of t. So, if we write it in this form, where we say that this is known, if we say that, then this continuous system given by u x of t transforms to single degree of freedom system with z 0 of t as the only unknown. Now, if that becomes, then the question here is that I should know xi of x. So, let us look at a specific problem. Let us look at a situation where let me take the cantilever itself, and let us say that how do I write it in terms of this. So, let us look at what happens. Okay. By and large, what does xi x have to satisfy? Xi x is anything which satisfies geometric boundary conditions and is unit corresponding to Z0 of t. Okay. So now if I look at it in this particular case, what kind of a xi x would I have? What are the geometric boundary conditions? The geometric boundary conditions are that u at u at 0 t is equal to 0 and u dash 0 of t is 0. Displacement in this direction is 0 and the slope is 0. So, xi x is unit here, okay, and has to satisfy the fact that, so in other words, this becomes xi 0 is equal to 0 and xi prime is equal to 0. Okay. These are the only two that they have to satisfy, and if that is the case, then all we have is, well, look at it, xi x equal to x by L squared. That satisfies the boundary conditions, because look at it, if I put x equal to 0, I get 0. If I differentiate it, I get 2 x upon L squared. Put x equal to 0, you get 0. So, this is valid, right. Xi x 1 minus cosine pi x by 2L. Well, let us look at this. If I put x equal to 0 here, it becomes 1 minus 1. So, it becomes 0 and I differentiate it. So, then what does this become? This becomes sine pi upon 2L sine pi x upon 2L. That is what happens. Put x equal to 0, this becomes 0. So, this is also an equally a valid system. Then xi x is equal to 3x upon L cubed minus 2x upon L squared. If we consider this as my equation, this also is valid, because note that this is a higher order than this, obviously it will satisfy. Okay, sorry, this is 3x squared minus 2x L cubed. Now, obviously, if you put x equal to 0, this disappears. Then you differentiate it. What do you get? You get 6x upon L minus 6x x squared upon L cubed. So, if you put x equal to this, it becomes 0 minus 0. So, this becomes 0. Okay. So, all of these are all valid, and note that all of them at x equal to L, let us look at x, it has to be 1. This obviously x equal to L is 1. Put this x equal to L, this becomes L upon L 1 squared minus 2 1. Okay. Let us look at this. Put x equal to L. What happens? Cosine pi over 2. What is cosine pi over 2? 0. 1 minus 0 is 1. All of them satisfy the geometric boundary conditions and is unit. So, all of these are valid. Which one is exact? Well, to find out which one is exact, we have to actually solve this continuous problem. Later on in the course, we shall be looking at that problem also, and we will see what would happen as the exact answer to this. None of these, by the way, are the exact solution, because note that under any kind of load, the xi x actually becomes a completely different. So, it does not matter. And note that under a load, whatever you get, and under the inertia force, you get different. So, all of these are equally valid, and all of them are equally approximate. Okay. So, this then becomes the fact that this is how, by defining any arbitrary shape function, I change the problem into just Z0t. Now, the question is that, okay, so if Z0t is the degree of freedom, then obviously my equation has to be of this form: m star Z0 double t C star Z0t plus k star Z0 is equal to p star t. And this is the equation that we have to get. Now, note that in this particular case, I am going to drop this term, because remember that we had said that, when I looked at rigid body assemblages, I put in dashpots, etc. Okay. And now, in a cantilever, you don't have dashpots. So, for now, I will just drop this term, and what we will see is, we will see if we can derive these, this and this for the specific kind of a deformable body. Okay. So, let us look at this situation. So, I am saying that I have this, okay, and let us say that this is E I is its flexural rigidity and m bar is the mass, okay, and let us say that it is subjected to a load which is given in the following format. I will say that the load is given as zeta x into p naught of t. Okay. In other words, what we are saying is, okay, remember, if it is a uniform load, what is zeta x? Well, its zeta x is nothing but 1. Okay. So, this zeta x looks at the variation of the load, and this defines, this is the load per unit length, which defines the intensity at a particular point. So, this then is typically how this load per unit length is defined. Okay. So, this is typically how a dynamic load looks, because the T variation is independent of the other variation. Okay. So, because it is typically like what, sin omega t, or it's it's some harmonic, or it's some pulse load, all of those kinds of things, but a unit load. Okay. So, that is why I am saying that this gives you the spatial variation, and otherwise it is this thing. Okay. So, this is how this entire thing is defined. So, E I is the thing. Now, how do we solve this problem? Well, let us see. Let me give it a displacement, and the displacement is where this is Z0 t and u x of t is equal to xi x Z0 t. Okay. So, this is my displacement at a particular point. So, if I have displacement at a particular point given by this, the inertial force is automatically equal to m bar dx, which is an infinitesimal length at a distance x. So, that is m bar dx into u double dot x of t. Okay. So, that is the inertial force that you have. Okay. What about due to the flexure, what kind of a load is set up over here? If you look at the internal force, or should I say, I will call that spring force, and that is actually mx at a particular point. Mx by definition is given by E I into del squared u by del x squared. Okay. So, that is the flexural moment due to this displacement. Okay. And well, that is it. I mean, let us just go with these are the forces. Now the question then becomes that okay, we found out the forces under the deformation. Now, what do we do? Well, the best way to do is write down an equation of equilibrium, because ultimately if you look at this looks like an equation of equilibrium, and we already looked at last time that you can use the principle of virtual displacement to solve this particular problem. Okay. So, then how do we get that? Well, let us see. Virtual displacement look like, I will give it a virtual displacement, where virtual displacement is, note that this does not vary with x, because there is a virtual displacement, right. So, those are the forces undergoing this virtual displacement. And what kind of a virtual displacement pattern do I give? Well, I will give xi x into del z 0, right. In other words, over here this is del z 0. I will give the same, this will be given by this, because even if when I give it a virtual displacement, the pattern has to remain the same as the previous one. Okay. So, let us see what do I get. Well, the work done by the inertial forces into del u x is going to be equal to m bar dx u double dot x of t into del u x, and this is for infinitesimal. So, we have to go from 0 to, this is 0 and this is L. Okay. So, it has to go from 0 to L. So, what does this become? Let us substitute all of these terms. See, u x of t is given by xi x z 0. So, u double dot is going to be equal to xi x into z 0 naught. So, this is going to be equal to z 0 naught t, that goes outside, and del 0 is del 0. So, this goes outside, and inside what do we get? We get 0 to L m bar. Now, one of them is xi x coming from z 0 and the other is del u xi x. So, I basically get xi squared x dx, and that is the work done by the real inertial forces undergoing the virtual displacement. Okay. So, this is what we get over here. Now, let us look at the next step, and which is the work done by the bending moment undergoing the virtual displacement. Okay. And if we look at that, then this is what happens. Let us look at what happens in the next term. A moment m x. So, the work done by the m x is going to be equal to del theta x. Okay. Note that this is m x into del theta x. Now, this del theta x is actually equal, not del theta x, but it is equal to, in other words, if I look at this is my dx. Note that I have mx here and mx here, and note that what we have is that I have mx and mx. So, if you look at it, this particular term, if you look, I am going to draw it larger, you will see that this is equal to, if this is my del d theta x, right. This is the, so then the work done is actually mx into del d theta x by dx into dx, right. That is what we have, because if you look at it, this del d theta x is going to be equal to over length dx, whatever the rate of change of the rotation, that is given over here. Okay. Now, M, if I substitute, this is the work done by the internal forces. So, if I look at Mi is equal to Ei into xi prime z of t, because again if you look back, if ux of t is given in this form, u double prime, that is del u x of t by del x squared, is going to be just the di phi prime by dx squared into z naught. Di phi is given by xi prime. Okay. So, this into zt is my mx, and this one, if you look at it, is going to be equal to, now what is d theta by dx? D theta by dx by definition is del squared v by del x squared. So, this entire thing becomes then nothing but xi prime into del z0 into dx, and this is for an infinitesimal. So, this entire thing has to be from 0 to L. So, if you look at this, this is going to be equal to z of t del 0 to L ei double prime x the whole squared dx. This is the work done by the internal forces, and now let us look at finally the work done by the load. Now, the load is what? At any point the load is given by p bar x of t. Okay. So, now if you look at this p bar x of t, so then the load is given as p bar x of t into dx. That is the load per infinitesimal length, that is the load, and what is the work done? It is equal to del u x. So, if you look at this, this is equal to p bar x of t into xi x dx 0 to L, because this is obviously integrated, and I have del z 0 here. Okay. So, now the question becomes that, look, the work done by your external forces is always positive, and the work done by the internal forces is always negative, because, so that is why this one actually becomes something like this. Okay. So, the external forces are these, and the internal forces is the work done by elastic forces, which is the bending moment, and the work done by the inertial forces. So, putting all of those down, I get this. Integrated from 0 to L m bar x xi squared x dx into z0 del 0 plus integral from 0 to L ei x dx into z0 del 0. These are the internal forces, and the work done by the external forces is 0 to L p bar x of t xi x dx. So, in other words, if you really look at it, this is, all of them have del z 0. So, that I am just going to eliminate that, because del z 0 is an arbitrary displacement. So, this term is my m star, this term is my k star, and this term is my p star. Okay. So, the final equation then becomes m star z Okay. So, that is what happens over here. So, now the question then becomes that this is the equation of motion, and my m star, I will just rewrite these terms that we have looked at. We will just describe these. If you look at m star is equal to 0 to L m bar x xi squared x dx. K star is equal to 0 to L ei xi prime squared x dx, and P star is 0 to L Okay, now if you look at this particular thing, you will see, excepting for this and this are things that we have developed already for the generalized single degree of freedom system, which was for the rigid body assemblages, right. These are exactly the same as that. Now, the question then becomes, is that this is the only term that comes in, and this comes in due to the deformation. In other words, when you deform a body in this form, it tries to go back to this. So, in a way, this is like a spring constant, equivalent spring constant that represents the inertial, the elastic force that comes from the that comes into the equation, because K star into Z. So, K star is like an equivalent spring force. Okay. Now, having developed this, let us now try to solve this problem for a specific case. Let me take the specific case. I am going to put a UDL on it. Okay. And then I am going to put this as my degree of freedom. Okay. So, this is P bar T. In other words, it is a constant, it is not a function of x. Okay. And I have E I and m bar also as constants. In other words, what we have is that this is a uniform bar with uniform distribution of mass subjected to uniform distributed load, and I want to write down the equation of motion in terms of this, and I shall use xi x to be equal to x upon L squared. I am assuming xi x to be equal to x upon L squared. Okay. So, if I do that, well, let us see what does the equation happen in terms of this. Now, without going in, let us go and look at the way we have developed it. So, if you look at it, this was m star is equal to 0 to L m star xi x squared dx, right. So, if we look at this, what does this become? M star is a constant, m bar is a constant. So, m bar goes outside and this becomes 0 to x, and this is xi squared. So, this becomes xi L fourth dx. Okay. So, this becomes m bar L fifth upon 5 L fourth. So, this is equal to 0.2 m bar L. Okay. So, my m star is equal to 0.2 m bar L. Now, what is my K star? My K star is equal to 0 to L E I okay. So, if your xi x is equal to x by L squared, then xi prime x becomes 2x upon L squared and xi double prime becomes 2 upon L squared. So, if I just do this, so 2 upon L the whole squared, this basically becomes k star is equal to E I 4 E I upon L fourth 0 to L dx, which is equal to 4 E I upon L cubed. So, that is my k star, and what is my p star? My p star is going to be equal to 0 to L p bar xi x dx. So, p bar goes out 0 to L x upon L squared dx. So, this becomes p bar L cubed upon 3 L squared. So, this becomes 1/3 p bar L. Okay. So, this becomes this. So, ultimately what is my equation look like for that this particular problem? It looks like this: 0.2 m bar L z naught plus 4 E I upon L cubed z naught is equal to 1/3 p bar L. Now, let us look at the units that we have. M bar L is mass units, because m bar is mass per unit length, m bar L is mass per unit. Now, E is Newton per meter squared, I is meter fourth. So, this becomes Newton meter squared by meter cubed become Newton per meter. So, this is units of a linear spring constant, Newton per meter, and P bar L is load. P bar is load per unit length into L is load. So, you see this entire thing, this is my k star, this is my m star, and this is my p star. Let us look at something interesting. What is the free vibration frequency going to be equal to? It is by definition k star upon m star, and this, if you look at it, is equal to 4 E I upon L squared divided by this. This basically becomes 0.2 goes up. So, this becomes 20 E I m bar L fourth. Okay. So, now let us look at this Newton meter squared, this is kg meter fourth. So, if you look at this, this basically becomes radians per second square root. This basically becomes per second squared, and if you look at this, this is. So, this is my, if I use xi x equal to x by L squared, my omega turns out to be this. Now, is this the true frequency, first frequency of vibration of this particular cantilever? Well, no. Why? Well, this is an approximation. The approximation, it is an approximation to the true value. Okay. Now let us look at another situation. Let us look at using the 1 upon x by L as my value. Okay. So, if we look at that, then what we get is, so I am going I have just used xi x equal to x upon L the whole squared. Note that all three that we have defined before are equally valid in terms of equation, I mean as a shape function. Okay. So, xi x is known as a shape function, by the way, because it defines the shape with unit amplitude corresponding to the degree of freedom. Okay. So, that is why it is called the shape function. Xi x is the shape function. Okay. So, now let us look at the same problem, accepting that I am going to define xi x to be given by 1 minus cosine pi x upon 2L. Okay. I am going to define this as my shape function. Why am I doing 2? Because I want to show you that whatever this equivalent single degree of freedom that I get is actually an approximation. Okay. Note that earlier when we looked at for the specific things about the generalized single degree of freedom with rigid bar assemblages, those were exact single degree of freedom. The xi x was unique. Okay. Here, you know, xi x, all that it has to satisfy is it has to satisfy the boundary conditions, and it has to satisfy that corresponding to the degree of freedom it is 1. So, that is all the shape function has to satisfy. Okay. So, let us see, plug in xi x equal to, and let us see xi prime is equal to pi upon 2L sine pi x by 2L, and xi prime is equal to pi upon 2L the whole squared cosine pi x upon 2L. Okay. So, these are I am deriving these up front, and also the fact that m star is equal to, remember, m bar x xi squared x dx, k star is equal to 0 to L e I x xi prime squared dx, and p star is equal to 0 to L p bar x t into xi x into dx. Okay. Given that, let us now try to find out what values do I get for with this xi x. Okay. So, let us try to find out m star. So, now m bar comes outside because it is a constant, 0 to L 1 minus cosine pi x whole squared dx. So, therefore, what we get is equal to, now this becomes what? This becomes equal to m bar one minus 2 cosine pi x by L plus cosine squared pi x by 2L. Now, note that cosine essentially, if you look at it, becomes nothing but, well, I am going to use another this thing, and that is that I know that cosine 2 theta, I am going to define this, is equal to cosine squared minus sine squared, and note that since this is equal to, see, cosine theta, if I subtract 1 from this, if you look, well, anyway, let me rewrite this. This becomes 1 minus cosine pi x. Remember that? Okay. This is 1 minus. So, what you get is, you get it equal to 2 cosine theta minus 1. And so, if you look at this, cosine squared theta becomes half of cosine 2 theta plus 1. Okay. So, I am going to plug that in. So, what that's going to be equal to? This implies that this is equal to m star 0 to L 1 minus 2 cosine pi x upon 2L plus half of cosine pi x upon L. Note that 2 of this is equal to this plus 1 dx. So, if you look at that, what we get is this is equal to, so m star becomes equal to m bar 0 to L. This becomes 3 by 2 minus 2 cosine pi x upon 2L plus half cosine pi x upon L. Okay. So, this is what we get, this into dx, and if you look at this, this becomes m star, and then inside I am going to put 3 by 2 L, okay. Then minus, now let us see, when I differentiate this, this becomes 2 L. So, this 2 and 2, this becomes 4 L upon pi, and this integration becomes sin pi by x. So, if you look at x, this is going to be 0, and when you do this, you get sin pi by 2. So, that becomes 1. So, this is minus 4, 1 by 0, and plus on this side again you have L upon 2 pi, and look, this is cosine. So, when I integrate this, I get sin pi x upon L. So, when I put x equal to L, I get sin pi is 0, and so both are 0 minus 0. So, what I get is equal to 3 by 2 minus 4 by pi. Okay. So, this becomes 3 by 2 minus 4 by pi m bar L. And if you look at this one turns out to be equal to 1.5, and this particular one, okay, this anyway, let us just leave it in this fashion. We will derive this later on, but you will see that 3 by 2 and 4 upon pi is approximately about 1.32. So, this is going to be about 0.18, about 178 L. So, this is approximately about 0.18 m bar L. Okay. That is what you get. And if you look at K star turns out to be equal to EI 0 to L xi squared double prime squared dx. So, this becomes equal to EI into 0 to L, and xi double prime we have already done. Xi double prime was equal to pi upon 2L cosine pi x upon 2L the whole squared dx. So, this is going to be equal to pi squared upon 4L squared. So, I am going to take that outside. So, this is going to be equal to pi squared EI upon 4L squared into 0 to L cosine squared pi x upon 2L into dx, and this we have already seen what this is equal to. This is equal to pi over 2 EI 4 upon L squared is equal to, this one becomes half and half, the other one disappears. So, this is going to be equal to this into inside is going to be equal to half. So, L by 2 plus L by 2 pi 0 minus 0. So, what we ultimately get is equal to pi squared EI upon 4 L cubed, which is equal to approximately about 2.4 or thereabouts EI upon L cubed. And if you look at this, if I look at omega, it is going to be 2.4 divided by 0.0 m bar. So, it is going to be EI m bar. So, if you look at omega, it is going to be equal to k star upon m star, and this is going to be equal to approximately just over 20, about 22 EI upon m bar L fourth upon 10. Different. You see that this value is different from what we have got earlier. Okay? And if you look at it, so in other words, because why should it be different? They are both approximations and they are not the same shape function. No way. Okay? In the case of this thing, you saw that the xi prime was a constant. Here the xi prime varies with cosine. Okay, so obviously they are not the same function. Let me finally get the p star. Since we are being complete, let us also do the p star. P star is 0 by L p bar into cosine pi x upon 2L d. So, this becomes p star 0 to L cosine pi x upon 2L dx. This is equal to p star into 2L upon pi sine pi x upon 2L 0 to L. So, what we get is it is equal to, I am so sorry, this is 1 minus cosine. So, there is a 1 minus cosine. So, there is a 1 minus. So, this basically becomes equal to p star into 1 minus it becomes L actually L upon 2 pi into L. So, this is equal to pre prime 1 minus 2 upon pi, which is equal to 0.2687 p bar L. Okay. So, the equation then becomes the following. It becomes (4 minus pi m star plus pi squared E I upon z double naught 0 plus pi squared upon 4 L squared Z0 is equal to 0.2687 p bar p naught upon L. So, this is what we get as our definition of this thing. So, this becomes essentially this point exactly becomes equal to this is 0.7313. So, this becomes 1.5 minus 2 times. So, this becomes 4 upon pi becomes 4 upon. So, this becomes 1.4. Okay. We will do this later. I'll get you exact values for this. The question then becomes that this equation that you get for which xi x equal to 1 minus cosine pi x upon 2L, this is the equation that you get. Looks completely different. Okay? This is, in other words, what we are looking at. I shall leave it up to you to do the 3x upon the other xi x term that I had given, that is 3x upon L the whole squared minus 2x upon L the whole cubed. That xi x, I will leave that as an exercise for you to do. Okay? So, I shall stop over here. Thank you very much. Bye.